Energy cannot be created nor destroyed.
Okay, energy cannot be created, nor it can be destroyed. What else do we know about the first law of thermodynamics? So you are right on that one. What else do we know so far about the first law? So you're right that energy cannot be created, nor it can be destroyed. The second thing is you can convert one form of energy into the second form of energy. You can do that, right? So that is allowed, right? So for example, you can transform your mechanical energy into electric energy. You can transform electric energy into heat energy, and you can do those kind of transformation without violating the first law of thermodynamics, right? So energy can be converted from one form to another form. That's an important piece of information. Now, when we say that energy cannot be destroyed nor it can be created, can we say that the total energy in this universe stays constant because we cannot add energy into the universe nor we can destroy it? So total energy in this universe stays constant. We can say that? You see what we on the chat box. Okay, so what do you think, guys? Let me write down here. So total energy of the universe stays constant. Now, where we got this universe from, right? I mean, the moment we say universe, our understanding is about everything, including the stars and everything you see up in the sky. And actually, it is true because system, which is basically under observation, plus the surrounding or environment is essentially equals to the universe. What do we mean by that? Suppose you are doing a reaction, right? And you're observing one particular part, of a universe, right? So that becomes the system. Say, for example, your reaction vessel is a system where the reaction is happening. Everything around it is environment. So when we say everything around it, where do we stop? Should we stop in the lab? So if I'm doing a reaction on a hot plate right here, and if this is the system, can I say only this part is the surrounding? Can I say this part is the surrounding? Or can I say this part is the surrounding, or entire lab is the surrounding, or entire building is the surrounding, or entire universe is the surrounding? In fact, the whole part, the remaining part, is actually environment. So if you add system plus environment, that is equals to the universe. Make sense so far? So when we say total energy of the universe stays constant, it's because suppose if I have an exothermic reaction, my reaction is giving out heat, but then this heat is being added into the environment. But then when I add the energy of system plus environment, that should stay constant. But then the environment is everything besides the system, and it includes everything from here all the way to the galaxies, all the way to the edge of the universe, which we have not even seen. It includes everything, right? So system plus environment or surroundings. In fact, some of the books will use surroundings instead of environment. So just to let you know, so energy of universe stays constant. This follows from the first law of thermodynamics, right? The next part that we studied in our chapter on thermochemistry, that was about enthalpy. What do we mean by enthalpy? Anyone? What do we mean by enthalpy? So how are heat and enthalpy different, or are they same? So this is just a recap going on, guys. Anyone? It's not the same. That's right. It is not the same. Enthalpy is a total heat. There is one piece of information missing. It is equivalent to total heat, which is constant. Okay, but then there's, so let me put it in this way. Okay, let's see. Heat is absorbed or released during, yes, you are right, Gabriel. Heat is absorbed or released during a chemical process, but that enthalpy is related to heat. But then those changes occur under special circumstances. So first of all, heat absorbed or released. That's one important piece of information that is related to enthalpy. But then there is one more, a very, very important piece of information that should be there when we are talking about enthalpy. What do you think? Okay, so heat absorbed or released by the system, that is right. So we need to have a system for that, right? So basically what you're saying is that we should be focusing in a particular area of study. For example, a reaction vessel, we are looking at that. So you are right in that. So enthalpy is related to heat absorbed or released by the system. That's true. But then we can have also enthalpy absorbed or released by the surrounding, right? So that is also true in that case. But then there is one still more crucial piece of information. That's right. Um, internal energy and product of its pressure and volume. Okay, so there is, so here I can see one chat information that I can see here. It is sum of the system's internal energy and the products of its pressure and volume. That is true. But then when you say the products of its pressure and volume, something is there in that product of pressure and volume. What exactly is that? This process need to occur at constant pressure. These two, if these two pieces of information are true, then you are referring to enthalpy. Now, where do we see that? In any chemical reaction that we do at a normal pressure, that means at a room, at 1 atmospheric pressure, the heat changes that occur are related to enthalpy. They are heat changes are enthalpy changes, right? So in that case, delta H, which is the change in enthalpy, equals to Q. And many times we will write here P because this tells you that the pressure is held constant. Now, this comes directly from your example that we did in thermochemistry. Okay, now in this chapter, besides enthalpy, I'm going to introduce one more term. Now, you know what enthalpy is. Enthalpy is the heat change which occurs at the constant pressure, right? Okay. Now, there's another term. We call it entropy. How many of you have heard this term? Many times I will use this term while we are about to leave, right? So you might have seen, I would say, let's increase the entropy. You might have seen, you might have heard from me many times before, right? Or I will say, let's disperse, let's increase the entropy. But then what exactly is entropy? Can anyone tell me what exactly is entropy? Might have gone through the video, right? Any definition, just let me know. What do you know so far about entropy? Let me see, what do we have? Disorder related to system. Example, ice melting. That is true. By the way, the video was not there for this chapter? Oh, wait a minute. This was
I don't
supposed
believe
to.
I watched anything on this.
Yeah, okay, because this was supposed to open in the morning today. Well, okay, that's fine. So let me see. Do you see that now? On your end, do you see? So you should be able to see the two videos on your end, right? So it says chemical thermodynamics 1 and chemical thermodynamics 2. You'll see that one. Okay. So what you can do is you can watch the videos and do the quiz before coming to the next class. But then today I'm going to go through this anyways, so don't have to worry about this. Okay. So one definition was disorder related to the system. You are right on that. So in some books, it will say randomness. Instead of disorder, they will say randomness. And both of them are true, right? The example which you guys mentioned on the chat is melting of ice. That's true. It's basically that. Now, the question is, when we think about the disorder, right? Is it a spontaneous process or basically it's a non-spontaneous? When I say spontaneous process, that means it happens by itself at, under a particular set of conditions. Say, for example, you have a block of metal on the top, you put it to the edge. Will it fall by itself or you have to push all the way down? What will happen? What do you think? Let's say, for example, you have a hill or you have a mountain, and water on the top of the mountain. Does it flow by itself, or you have to push the water all the way down? That's right. So once you push it, on the edge, it just falls by itself, you know. So when we talk about this metal object, when it's on the edge, it will fall by itself. Water flows from the top of the mountain at the bottom by itself. You don't have to push it all the way down. See, those processes are spontaneous processes. You don't have to do anything over there, right? Water will find its way down, right? Because energetically, that is favorable process, right? Okay, so those processes are spontaneous. Now, if I want to take this metal block at the bottom and if I want to move it to the top, is it spontaneous? Will it simply just move up by itself? Answer is no. You need to supply energy. You need to take this block, use your energy, and go up the building, right? So just like if you want to put the water on the top of the mountain, you need to use a pump. You need to use a water pump, and you need electricity for that, right? So those processes are not spontaneous, right? So the processes which happen by themselves under a given set of conditions, those are spontaneous processes, and the one which require energy under exactly the same conditions, if you need energy to do those processes, those are non-spontaneous processes, right? Now, entropy is related to spontaneity. Now, what do I mean by that? Let me share one simulation with you. This one is a good one, actually. I liked it. So I just thought of sharing with you guys. Just give me a second. So all of you can see my screen?
Yes.
So
Yeah.
you have a gas in one chamber, and in second chamber, you don't have anything. It's a vacuum. It's a pure vacuum. Nothing else is there, right? And I'm going to remove this barrier from there and see what happens. Simple as that, right? So before I start, what do you expect? If I simply remove this wall, what would you expect? So these are the gas molecules. The blue dots are the gas molecules. And here you can see the graph, and you'll see what happens. I remove the barrier and see what is happening. You are seeing on the left chamber, you are seeing the distribution of molecules, and see what happens. We'll wait and see. That slowly reaches an equilibrium. That's right. That is true. It is trying to approach this red line, right? And if I run for more simulation, more iteration, it will eventually touch this red line and stay there, right? Now, why is that? Because when you remove the barrier between, you know, when you, okay, so when you remove the barrier, the gas will spontaneously expand into the vacuum. You don't have to supply energy, right? Because you gave these molecules some extra space to move around, and they will move around in that space because you just gave them that space, right? Eventually, you are going to see an equilibrium. That's what you mentioned right there in the chat. So Kaylin mentioned that slowly reaches equilibrium, and that's absolutely right, right? So can we say that entropy is related to equilibrium? What do you guys think? After all, we have reached equilibrium. Both the chambers have the same distribution over the time, right?
Yeah, the answer I would say is yes.
So in a way, can we say that it is related to equilibrium? So indirectly, it is related to equilibrium, but in a different way, because when we go through the Gibbs free energy, delta G, that's what is related to the equilibrium. And we'll see that, right? There's an equation for that. But now you can see here, Abram, we are thinking about not everything relates to equilibrium. Every system tries to reach it. Yes, that's true. Every system tries to get to that equilibrium point, right? But then here, that's not we are focusing on only entropy, right? Here we are focusing on entropy. That's the property that we are studying here, right? So can we say work done? It attempts to get to the equilibrium? No. Is it related to equilibrium? Answer is yes, right? So when we make a blanket statement that everything is related to equilibrium, then we got a problem there, right? Because when you directly equate it to that one, as I said about the work done, it's not directly connected to equilibrium, right? But then there are equations where you can convert your work into energy and then you can relate it with equilibrium. Those two are different animals. Make sense? Okay, so let me do one more iteration for you guys. Let's say we have two gases, left and right. We have, say for example, on left side, we have hydrogen, or say for example, we have nitrogen, pure nitrogen on the left side, and we have pure oxygen on the right side. What would you expect in this graph, the one that you see at the bottom? What would you expect for these two chambers to go through? If I remove this barrier, what would you expect? Would the gas on the left stay blue, the gas on the right stay blue, red? Would you expect that? No. So can I say that the moment I remove this barrier, these two gases are going to mix themselves spontaneously? Yes, we do say that, right? Now let's do that. Let's see if it really happens. Look at the bottom. The blue side is going to the red side, and you can see, and red side is going to the blue side. So here our area of focus is on the right chamber. That's what we are saying. So the number of molecules, red molecules are decreasing. The number of blue molecules are increasing. And at a particular moment, you're going to see an equilibrium, right? But then while it is attaining that equilibrium, we are seeing randomness. Because before that, the system was organized. We had blue on the left and the red on the right. But now system is getting random. It is getting more and more disordered, right? So this is connected to entropy. And you'll see eventually they will just merge at this line where you have 50-50% chance of getting the molecules on the left and molecules on the right as same. See, again, here we are looking at the probabilities. When we say 50-50% chance of having blue on the left and blue on the right, here we are talking of the probabilities. So the next part that we're going to do is think about the disorderedness related to probabilities. And if I just run more iteration, here we just ran 800. If I just run more, these two lines will merge with the central line, which is equal mixture. Okay, so let me go back to the slides where we were. So now you know that in a spontaneous process, disorderedness increases. So I can say entropy increases, so this is the sign of increases with randomness. And entropy, what can you say about the spontaneity? If entropy increases, what happens to the spontaneous nature of a reaction? Does it increase or decrease? Guys, just write down in the chat box so I know.
It would increase.
That would increase. So when entropy increases, it increases the spontaneity, right? So those two are connected directly because entropy is connected to the randomness and randomness is connected to spontaneity. Okay, having said that, let me give you one example. And let's try to think about entropy in terms of probabilities. Let me paste one. And by the way, you can find it. You can find this in your book as well. I'll just go on the next slide. So we have the chamber A filled with gas, chamber B in vacuum. You open it, spontaneously, you're going to see the gas gushing from left to right, and you will see an equilibrium established. And this process is a spontaneous process. Removing all the molecules from chamber B is not spontaneous. You need to supply energy. You need to apply a vacuum pump to do that, right? So again, that one is from your book, so you can see that. And the second thing is about this diagram. This is also a very classic diagram of entropy, right? You have an egg and you drop it and it breaks down. But then this is a spontaneous process, right? You are increasing the disorderness of the system. You can see over here. Now to go from here back into that, is it possible?
Nope.
How many of you think it is not possible? Just write down in the chat box. Are you sure, Abraham? See, let's see if, okay, not possible. I'm looking for one word. Let's see who uses that word.
Not spontaneously.
Okay, I'm still looking for one more word. Let's see if anyone uses that word. Let's see.
What, that it would require energy to do so?
Okay, you are trying there. Okay, energy to do so. But I'm still looking for, let's see. Not within our system. Okay. I'm still looking for one more thing. I just used that word a few minutes back. Let's see who uses this word. See, there's a big difference between not possible and that word, the one that I'm looking for. Let's see who uses that. Any guess? So when you say not possible, how sure you are that it is not possible? Guys, can you hear me? Okay, Abram, you are getting there. Okay, you just used that word in a different way. I'm just looking for that one. You just used it. So when you say unsure, that means less likely. See, when we say about 100% not possible, and when I tell you less probable, those are two different things, right? So if I give you a billion chances or a trillion chances, will is there any 1 in 1 billion that this can be done? Or 1 in 1 trillion it can be done? Or 1 in a billion of a trillion if it can be done? Answer will be yes. The chances are very less, but it is possible. See, now we are talking about spontaneity in terms of probability. That's the term I used before, probabilities, right? So entropy is all about probabilities. And you are going to study that once you are into the higher level classes. You will study statistical thermodynamics, right? It is not the classical thermodynamics that you are studying now, but then it's a statistical thermodynamics where you invoke the probabilities into the randomness, and you are going to see so many amazing things. It's like mind-boggling things, right? I mean, I can spend hours, discussing about that, but then this is not the, the course where I should be doing it. But then it's really, really a beautiful, I would say, science when we think about the statistical thermodynamics, right? But then there is a chance that it can happen, no matter how small that chance is. Just like we think that life is possible on Earth. That's true. Why? Because it's so intricate. There were so many things which happen at the same time to lead to the life. But then when you look outside in the universe, we have in our Milky Way, we have billions of stars. And then we have billions of galaxies, which have billions of stars. What is the probability of finding the life form in the known universe? Now that becomes a high probability, right? But then if our universe was only confined to the solar system, the probability is zero, because there is no way you can have so many reactions happening at the same time at the same place. But then given the enormity of the system, that can happen. Okay, so you will see that in upcoming example, what exactly I mean, right? So for now, the next thing I'm going to discuss is about a reversible and irreversible process. Now, what exactly is a reversible process? Well, let me paste one screenshot. This is taken from a book. Okay. Now, whenever I'm doing a change, say for example, my reaction, right, is giving out energy. That means the surrounding is absorbing that energy. All of you agree with that? Because if my surrounding is not willing to accept energy, then where does that energy go? That will stay with the system, right? So for a reaction to be exothermic, to give out energy, there has to be something out there to accept it, right? Now, when the process is built in such a way that those energy changes are too tiny, they are very, very small changes, very, very tiny changes, In those cases, the process is reversible. What do I mean by that? So suppose your system is giving out energy, X amount of energy, right, to the surrounding. If your surrounding in return gives the X amount, the same exact same X amount of energy back into the system, there is no change in the overall energy of the universe. It stays the same. Everything stays the same, right? Okay. But then if there is a big change, suppose if the system gives out energy, surrounding gains energy. But then if that change is really big, now if surrounding tries to give that energy back into the system, it may not be exactly the same. It may be less or it may be more, right? So those processes are irreversible processes. You cannot simply reverse those processes, right? Now, what do I mean by that? Suppose if you have at room temperature, if you have ice melting, all of you agree with that? If you have ice melting, what would happen? It will spontaneously melt into water. That means your ice is absorbing energy from the surrounding and it is getting converted into the liquid water. Now, if it was truly a reversible process, ice will absorb energy, but then it will also give out the same amount of energy at the same moment. That means that process is reversible. Ice will not melt. It will stay as in form of ice. So those processes are reversible, where those energy changes are really, really tiny, right? And you can have a irreversible process where the system absorb energy, changes the state, as I mentioned about ice melting. That would be irreversible process at room temperature. Now, you decrease the temperature at 0 degrees centigrade. That again is an irreversible process. Why? Because in this case, water is losing energy to the system spontaneously at 0 degree. And it's getting converted into ice. You cannot have liquid water at 0 degrees centigrade, right? It cannot happen. So just like at a room temperature, you cannot have ice. At 0 degree, you cannot have liquid water, right? So those processes have to be thought in terms of the context. All of you on the same page? Any guess or any suggestions which you may have about the spontaneous process? Can you guys give me one example of a spontaneous process or irreversible process from anywhere in the nature?
Could that be rust?
I'm sorry, what's that?
Could it be rusting? Rust?
Can you write it down in the chat? So that's true. That's true. Rusting, right? So under the normal circumstances, iron, metal, wants to get converted into rust. Why? Because rust is more stable than the pure iron. So it wants to go there. It's a spontaneous process. It's an irreversible process. You are right in that. You are right in that. Okay. Any other example from the real world situation? So just like water flowing down from the top of the mountain, right? It's an irreversible process. It just comes down. It doesn't want to go up. Burning wood, absolutely. So once you burn wood, you are converting your wood, which is less stable, chemically less stable than CO2 and water. So that would be a irreversible process. And you might have seen, we just draw arrow in one direction. We do not draw equilibrium arrows in those cases. It just goes from one side to the second side, right? So that being said, there is one interesting thing about irreversible process. Once, say for example, as you gave the example of rust, a fantastic example, you convert iron into rust, right? It's a spontaneous process. Now, if you want to go back, can you get exactly the same crystal that you had before it went to the rust? So what do I mean by that? Let me draw the crystal. I mean, I'm just trying to draw a simplistic version of that. So suppose I have a crystal like this, and suppose if I was able to number the iron atoms as if I was able to identify each one of them separately. We know that all of them are exactly identical. It's not possible, but then just think in this way. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now we have these 12 atoms and they form, I'll just move them here. Now they're rusted, right? Oh, wait, what happened? So I'll just draw another one. So they go under oxidation process. And now we have 1, 2, and we know in case of rust, it is like a powder. So, and I'll just put it in another color. So that way, I will put it in orange. So this is 1, 2, 3. Suppose this is rust, right? And it's form of powder. Now it may be that 1 is here, 2 is here, 3 is here, 4, 5, 6. Well, now we got rust. Now I'm converting rust back into, I'm reducing rust. That means I'm converting my iron oxide back into pure iron. And I can do that. I can simply use a reducing agent and I can remove oxygen from the system, right? That can be done. And I can get the crystal back. I can get the same crystal back. Only problem is that once I reduce this system, can I exactly reverse the state where I started from? Answer is no. Why? Because I can have 1 here, I can have 2 here, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. See, in that way, this system and this system, they are different because the way these atoms are arranged are different than the way we started. Although the lattice looks exactly the same, but then those atoms, if you were able to identify them, if you were able to have labels on them, they are at the different locations. So system did not go back to its original state. This is a very typical of a reversible process. Now, if it was a perfectly reversible process, I would have got the same system, the one that I started with. Make sense? All of you?
Yes.
Okay. Now, as I mentioned, entropy is related to the spontaneity, right? And there is an equation for that, right? So let me write down that equation. Since I defined the reversible and irreversible processes, because that's going to come handy in what we do next. So delta S, which is change in entropy. So S is entropy, and C delta is change. But then those changes are big and macroscopic changes, right? Which you can easily measure. Now, if the changes are small, then we convert this delta into derivative, which is D. And we'll go through that. So delta S, which is change in entropy, depends on entropy of your final step minus the entropy of your initial state. So S final minus S initial is the entropy of your system, right? The change in entropy of your system, right? But then this is also given by Q reversible by T. Now, what do we mean by that? Now think in this way. Whenever there is a process which is a reversible process, a perfectly reversible process, which can convert your system back into its original form, those are the reversible processes. Energy changes in those processes are given by Q, right? And Q reversible. And if you divide that by temperature, you get the change in energy of the system, right? Okay. Any doubts so far about this equation? Now keep in mind, we are doing those processes at the constant temperature. Now, to give you an example of it, suppose if I'm doing an exothermic reaction in a reaction vessel, that is giving out energy, a tiny amount of energy to the surrounding. And the surrounding in turn is giving back energy into the system. And my system goes back to its original form, right? But then whole process is happening at a room temperature, which is 25 degrees centigrade. Suppose in that case, the change in entropy will be the energy which is given out and absorbed back, that change in energy divided by the room temperature, which is 298 Kelvin, which is your room temperature. So far, so good? Now,
would you actually be able to repeat that last thing one more time?
which last thing? About this part or this part?
Well, I don't know. No. Yeah, the second part there at the bottom. I'm trying to think of exactly.
So suppose if you have a reaction, and suppose if that reaction is giving out energy, suppose that energy is X joules of energy, X joules. That energy is given out to the surrounding, and system changes its state slightly. Now, if surrounding gives back that energy into the system and your system goes back to its original form, that process is a reversible process, number one, and the energy change, which is X joules, will be given by Q reversible. And since I mentioned that you are doing that reaction at a room temperature, which is 25 degrees centigrade or 298 kelvins, I'm not changing that temperature. So my conditions related to the temperature, I'm keeping constant. So that temperature goes here. So the ratio between that energy, Q reversible, divided by temperature, gives you the change in entropy. Now, what is the okay? So what is the physical significance of it? Let's think about this one. Suppose you have a crystal. Highly ordered system, right? And I put it in a box. Now, suppose I start to heat it. What would you expect in terms of the location of these atoms? Are they going to change or they're going to be different? Suppose I supply energy. What would happen to these atoms?
They would likely change.
They would likely change, right? So they're going to move their position. If I supply enormous amount of energy, the whole crystal is going to melt, right? But then there will be some changes, right? So in terms of randomness, that's going to increase. But then why did that randomness increase? It increased because you supplied energy, number one, right? And number two is the surrounding. Why? Because it is the surrounding which is giving that energy to the system, right? So the temperature of surrounding, which is a measure of energy anyways, should be taken into account. That's why Q divided by T will tell you how much randomness you are expecting in the system. So if you do not supply, if you decrease the temperature, you will decrease the energy of the system, right? If you increase the temperature, you will increase the energy of the system. That you should understand, right? Okay. Now, given that, let's think about one more aspect about entropy. Now, just like enthalpy was a state function, enthalpy depended on only initial and the final steps. Entropy is also the state function. It only depends on your initial stage and the final stage. It does not depend on how you take your system through that one. So for instance, here in this case, suppose this is the entropy of system when you started with S1. Suppose this is entropy which is S2 for the rust. Suppose this is entropy of your final stage S3. The change in entropy going from step number 1 or stage 1 to stage 3 only depends on entropy of your stage 1 and stage 3. Does not depend on that you had a middle station which was the rust in between. Does not depend on that. It only depends on initial and the final steps. Now, it may happen that you stop your reaction at the rust stage. In that case, your entropy will depend on initial, which is S1, and the final will be S2, right? So keep in mind, entropy is a state function, depends on initial and the final stage of the system only. Does not depend on how you took the system from one step to the step, from initial stage to the final stage, right? So again, an important thing for you guys to know. Okay. Now, at this moment, I'm going to define the second law of thermodynamics. Now, you know about the first law. I'm going to define the second law. Second law depends on the entropy. What does it say? It says that the entropy of the universe increases spontaneously. Now, when I say increases spontaneously, we are referring to irreversible process, right? For a reversible process, entropy of universe does not change, right? So what do we mean by that? Let me go on to the next slide. Delta S, which is your universe, will be equals to delta S, which is system, plus delta S, which is surroundings. Now, first of all, this is true for reversible process. Why is that? Think about this. Suppose I have a system, right? And this system ends up absorbing X joules of energy. So I'll just put, say, for example, 100 joules of energy. So initial step, say, for example, S1 is, and suppose we are doing this reaction. Let me give you the temperature for that one, and then we can solve this problem in that way. I was just writing a short form. Suppose the temperature is 300 kelvins, and Q in this process, which is heat given out by the system, suppose that one is 100 joules. Can you tell me the entropy of the system based on the equation which I just told you? delta S was Q reversible by T. All of you agree with that? That's what we wrote before. So in this case, Q is 100 joules divided by temperature is 300 Kelvin. Can you tell me the change in entropy of the system? This is your system. 100 divided by 300, guys. What do you think is the answer? Guys, are you there or am I the only one?
0.333. No one else is going to mention.
Okay, guys, I need response from all of you. It's a thermodynamics. So that's going to be 0.33. I'll just put it like that, 0.33. Now, in this case, system is giving out energy. So when system gives out energy, that has to be negative. So in that case, my entropy gives out and it becomes negative, right? In that way, what happens to surrounding? Because surrounding is absorbing exactly the same amount of energy. So what happens to the surrounding? Well, in that case, delta S for surrounding, that's going to be equals to the same thing, which is Q reversible by T. In this case, it ends up absorbing 100 joules of energy at 300 kelvins. This is going to be plus 0.33 joules per Kelvin. But now, when I add delta S system plus delta S surrounding, what would you expect? See, system is negative 0.33 joules per Kelvin. Surrounding is positive 0.33 joules per Kelvin. What would you think now? What would be the answer? Negative 0.33, positive 0.33 is 0. So this tells you, but then what exactly is this term? This term is delta S universe. So there is no change in entropy of universe if you are dealing with a reversible process. Why is that? Because your system goes back to its perfect original state. There is no change in entropy of system. There is no change in entropy of surrounding. Added together, it goes to 0. Okay, now this is about the reversible process. But then what happens for an irreversible process? Well, delta S universe is still delta S system plus delta S surrounding. But in this case, it will not be equals to 0. In fact, it will be greater than 0 when you are thinking about irreversible process. Now you would wonder, why is that? Let's look at the example of rust that we started with. We started with stage 1, where we had atoms or arranged in a perfect lattice structure. But then we went to stage number 3. If that was our final step, we still got the perfect lattice. But then is it the same as we started with? First, answer me that question. Is system in its original state when we started with?
Not exactly.
Not exactly. So we started with a perfect lattice. Although on the right side, we have perfect lattice. Everything looks perfect, right? And it is perfect. But then the position of those atoms are different than what we started with. Now, why do we think that entropy is more for this process? The reason is you cannot go from S1 to S3 without going through the major changes of reorganizing these atoms. It cannot go back to its original form. It's simply not possible, right? So that's the reason why entropy of universe is greater than zero when you are thinking about irreversible processes. Okay, so keep that in mind. It's a very, very important concept to know. Now, having said that, let me go into something which is related to the statistical thermodynamics, and that would be when we think about the entropy on a molecular scale. Now, you can see this one in your book as well, and we're going to solve a problem on this. So suppose you have a system. We start from stage number 1, which is A. And you open the nozzle in between. And you just have 2 molecules here, right? You have 2 molecules, one in red, one in blue. You open the nozzle, and now you see 4 states, 4 probabilities. See, now I'm talking in terms of probabilities, right? So you have 4 probabilities. One of the probability is that blue stays here. The second probability is the red stays here. The third probability is both blue and red on the right and both blue and red on the left, right? Can you tell me, out of these 4 probabilities, which is the most likely probability, or which are the most likely probabilities?
Does it depend if one's positively and negatively charged?
No, I mean, just in terms of if both of them were neutral molecules. I think there is one answer. Yes, Abraham, you are right. Let's say, guys, you need to write down the chat box which probability or which probabilities would be most, I mean, which are the most probable states? Let me put it in that way. So let me put it in this way. So you have 2 chambers and you have 2 molecules, right? So you have 2 chambers and 2 molecules. So having the first possibility is 1/4. This is also 1/4, 1/4, and 1/4, right? So in that way, what is the probability of having these 2? See, having 2 on both the side is first of all highly likely. Getting 2 on one side and none on other side, it's only 1/4 possibility. So this is most likely. And when you think in terms of statistics, 1/4 plus 1/4 is 1/2. So there's 50% chance that each side will have 1 molecule. If these 2 molecules are the same, then there's a 50% chance. If these 2 molecules are different, then there's 25% chance that you have 1 molecule on one side, on the second molecule on the second side. But then this is a symmetric arrangement, having 1 molecule on both the sides. In terms of, think in terms of pressure, you have equal pressure on both the sides, which is an equilibrium situation. So the 50% chance of having that. And there's only 20% chance of having two on two sides and two on other side, 25% chance. So this is most likely possibility. Let me give you one more example. When we have more number of atoms, see, two molecules and two chambers, four possibilities. What if I have four molecules and two chambers? How many possibilities are we looking at? Any guess on that? Suppose if I have four molecules and two chambers, how many possibilities are we looking at? So let me put it in this way. Suppose this is the number of chambers. And if I raise it to the exponent, which is n, which is the number of molecules. In this case, I have two molecules and I have two chambers. So I have four possibilities like that. Suppose if I have four molecules and two chambers, how many possibilities are we looking at? 2 raised to 4. So each possibility is 1/16. So you are looking at 16 possibility. Here, each possibility, occurrence of each possibility is 1/4. In this case, it's going to be 1/16. So let me show you that one. And then we will see which is the most likely possibility to occur. So let me paste that one for you. And you'll be really surprised to see something amazing coming out of this. So now you see, we have 16 possibilities. We have four molecules and we have 16 possibilities. Now, can you tell me, what is the most likely possibility to happen? Very good. So you can identify right here. This is the most likely possibility, right? And what is the ratio of that? See, this one is 1/16. This one is 4/16. This one is also 4/16. This is 1/16 possibility of occurring that. So what can we say about this one? Six by 16. Now you see how that probability is increasing. Now you remember when I spoke about that egg and I mentioned that you can reverse it. It is just a matter of probability. So having that state is possible, absolutely possible. But then look at the probability of that state. If you have four molecules and two chambers, it's 1/16 already, right? So, but then it is there. It is not completely zero. You cannot have zero. Now, let me put it in this way. Think about another situation. This time I gave you two chambers and I have a gas in this. And this is 1 mole of gas. Can you tell me what is the probability of having every single molecule of gas on the left side? I have chamber A and chamber B. What is the probability of that? Of having every single molecule of gas on the left side in one chamber?
Not very high.
Not very high. Can you give me the number? In terms of probability, the one that I gave you before.
Would it be 0?
No. What is energy?
I don't know we know the moles. Oh, LOL. So this is Avogadro's number.
That's true.
Okay.
Can you guys imagine this number? Imagine this number, and then you divide 1 by that number. So you are right. It would be almost 0. But then there will be a number associated with it. So now I'm going to say it is unlikely, highly unlikely, it is highly improbable, but then no matter how improbable that may be, will be always 1 in so many chances that there will be one possibility of that, to have it in a spontaneous way. So all molecules, there will be one chance, and 1 divided by 6.02 10 to the power 23. That number, no matter how small that number is, no matter how ridiculously small that number is, there is always that 1 in that chance to have all the molecules on the left side, right? So, but then that number is too small, right? So it tells you in terms of probabilities that the molecules want to simply spread into both the chambers. The probability of that one will exponentially, in fact, it's going to be really a drastic exponential rise when you go from all molecules in A to the equilibrium point where both the molecules, both the chambers are equally occupied by these molecules. Right? So to put that into an equation, this is related to entropy. So to put that into equation, we use entropy in terms of probability. So delta S is K ln W. Now, what do we mean by that? Delta S, you already know. W is basically the number of microstates. So suppose when we go here, all of you can hear me, guys? I heard some sound. All of you can hear me, right?
Yes, Professor.
Okay. So here in this case, when we think about these ones, these are the microstates, right? So suppose this is my starting state and I go from state A to state C. How many more states do I see? I see 16 more, I see 6 more states. I start with 1, I end up into 6. So these are the number of microstates. Each one of them is a microstate. So W stands for that microstates that we are looking at. So when we think about having all the molecules on one side, which is on the left side, this is the microstate that we are looking into. This is the W that we are looking for, right? Okay, now what exactly is K? K is the Boltzmann constant. And the value for this one, and you're going to calculate that for me. I'll just put it here. N, which is your Avogadro number, multiplied by K equals to R. Now, what exactly is R? In terms of joules, it's 8.314 joules per Kelvin per mole. What is Na? It is 6.02 10 to the power 23 per mole. Can you find me K, Boltzmann constant, in terms of joules? Or is a gas constant? That's true. But then can you give me that number for the Boltzmann constant?
Is it 1.38 times 10 to the negative 23?
Yes, 1.38, 10 to the power negative 23. And the units for K would be the same unit as entropy. So joules per Kelvin, right? Because we just cancel out per mole. So this tells you, see, when we remove the moles, we are looking at the energy of one single molecule, right? So think in those terms, right? Okay. So this is the value for Boltzmann constant. It is a constant. Now you see delta S equals to K. You know the value for K. And if I tell you the microstates, you should be able to calculate the change in entropy. What do I mean by that? Let me take this example, put it here. Suppose your system is going from A to B. Delta S is equals to K ln W final, the number of microstates in the final step, minus K ln W initial. Can you find me delta S for this change? W here equals to 1. W here equals to 1, 2, 3, 4. Can you find me that one? I'll expand this so you can see the value for K as well in the previous slide and find me this answer. So W is the microstate. So how many microstates you started with? So in this case, you start with 1 microstate, which is A. You go to B, which is 4 microstates. So this is the macro state of your system. But then in that microstate, your molecules are constantly moving, right? So you can define it in terms of microstates, as I mentioned. So W is 1, you have 1 microstate, and this is 4, which is 4 microstates. You're going from 1 to 4. Can you find me this answer, guys? Okay, that looks correct to me. I already got the answer from Roberto. And guys, make sure you take a natural log. So if you are guys getting 1.91 10 to the power negative 23 joules per Kelvin, you guys are right on that. So essentially what we did here was delta S equals to K ln. And since log of A minus log of B is log of A over B, so I'm going to take ln 3 over 1. That's going to be my 3 mic. I'm sorry. Why do I keep on writing 3? Because it should be 4. So 4 over 1, that's going to be equals to, and we already know the value for K, which is 1.38, 10 to the power negative 23. And this is joules per Kelvin multiplied by, this is just a number. 4 and 1 are the numbers without any units. Is the number of microstates. So if you multiply that with ln 4, your answer would be 1.91 10 to the power negative 23 joules per Kelvin. So this is the change in entropy when you go from A to B. Let me show you that one. Can you find me the change in entropy when you go from B to C? This time you're going from B to C. Just put it here. Find me delta S for this change. It's going to be quite simple the way we did it earlier. Delta S equals to K ln W final minus K ln W initial. That's going to be K ln 6 because you have 6 microstates here, but you started with 4 microstates. That's going to be K ln 4. And what should be the answer, guys, here? So delta S was to 1.38 10 to the power negative 23 joules per Kelvin multiplied by natural log 6 divided by 4. So 5.6 10 to the power negative 24, that's right. 0.6 10 to the power negative 24 joules per Kelvin. That looks correct to me. Now, do one thing. Go from state number C. Let me see. Okay, wait a minute. Go from C to D. Go from C to D. So I'll take it here. This time go from here to here. And tell me the change that you're seeing. Again, S equals to K ln W final. Absolutely, that's right. Abram, you got it right. Very good. Roberto, you are also right. So it turned into negative, right? So now you got negative 5.6 10 to the power negative 24 joules per Kelvin. Now, did you just see what happened? We are moving from more random. See, this is a random system. That means The more number of microstates available to you of the same energy, more is a random system and better the system, right? Because this is where system wants to be. System wants to have more number of microstates. But now you're going from more number of microstates to the less number of, you are making system more ordered. See, here you have 2 molecules on either side. Now you have 3. To get 3 molecules on one side, less probable, right? So you are making the system more organized. So you see the sign, it becomes negative. So when entropy is negative, you are moving towards more ordered system. When entropy is positive, you are moving towards more disordered system. Isn't it that that's what we saw for a reversible process? Entropy increases. That means you have more disorderedness in the system. That's where the system wants to be. Going back here, let's see if we can prove that entropy is a state function. Okay, so going from B to C and C to D, let's do that one. You already did from B to C, which was 5.6, 10 to the power negative 24. I'm going to copy this one, and I'm just going to use the values that you got. So going from B to C, you are increasing the entropy, which was positive 5.6, 10 to the power negative 24. Going from C to D, that was negative 5.6, 10 to the power negative 24. If I go from B to C, C to D, what is the overall change in entropy, guys? If I go in a step-by-step manner, I add entropy of this plus entropy of that, entropy change in 0. Absolutely right. So from B to C and C to D, I go in step-by-step manner, I get answer 0. Now, suppose if I go directly from B to D, what happens in that case? Well, let's see if we get answer equals to 0. So this is going to be S equals to K ln W final minus K ln W initial. That's going to be K ln 4 over 4, which is basically answer ln 1. Log of 1 is 0. This turns out to be 0. So we just proved that entropy is a state function. So if my final step is D, my initial step is B, does not matter how I go there. I can go in step-by-step manner. I can still get answer 0, and I can go directly from here. I still get answer 0. This proves it's a state function. Okay, guys, so we will stop here for the day. And next thing, we will on Thursday, we will continue with this chapter.